Welcome everyone. Today we are diving into the world of atoms, the tiniest unit that still carry a unique chemical property of an element. Imagine that everything we see, whether it's a glass of water, the air we breathe, or even the metal in our phone, is constructed from these incredibly small building blocks called atoms. Each atom is like a tiny Lego brick that we combined in different ways forms all the diverse materials around us. This foundational concept is essential in chemistry because it helps us understand how substances interact, change, and form new compounds. So let's dive into it, explore how these atoms are structured and why they are so important in the world of science, important in chemistry and technology. And let's begin by revisiting the milestones in atomic theory. Among these early thinkers was Democritus, who proposed that matter is composed of tiny, indivisible units he called atomos. The very idea that everything we see is built from these small, fundamental pieces. Then in 1800s, John Dalton later provided experimental support for atoms as the fundamental unit of matter, show that each element is made of its own kind of atoms. Then in turn of 20th century, J.J. Thomson's plum pudding model suggested that electrons were embedded in a positively charged sphere. That is, by studying the property of electricity, found that atoms must contain even smaller elements that we call electrons nowadays. So plum pudding, because you can see here, it's pictured that atoms as a kind of positively charged soup with electrons sprinkled through, much like raisins or rye grapes in the pudding. So that's represented here. The true turning point came with Ernest Rutherford. Famous scattering experiments when alpha particles were fired at thin metal foils. Some were deflected at very large angles. The surprising result led Rutherford to conclude that an atom's positive charge and most of its mass must be concentrated in a tiny dense nucleus at the center, with electrons orbiting around it at a distance. Building on this nuclear model, Niels Bohr introduced a revolutionary idea: electrons travel in fixed, quantized orbitals around the nucleus. So this concept not only explained why atoms emit light at specific wavelength, as seen in hydrogen spectrum, but it also marked the beginning of modern quantum theory. Bohr's model helped us understand that behavior of electron is not continuous, rather it's discrete, but it occurs like discrete as it occurs in distinct steps or jumps from levels to level, so between energy levels. This understanding of distinct energy jumps or distinct jumps between energy levels is a key to semiconductor industries nowadays, and for the many devices that we use or that we currently watching today. And now let's take a much closer look at what makes up an atom. Picture the atom as a tiny miniature solar system. At its very center, the nucleus, a compact dense core that holds two types of particles, protons and neutrons. Protons are positively charged particles. They are like the identity cards of the atom because they determine atomic number, which tells us exactly which elements we are dealing with, right? Neutrons, on the other hand, have no electric charge. They are neutral but still add significant weight to the atom, means they are heavy. So now imagine a swirling cloud around that central nuclei. That's where the electron comes into play. They are very small, negatively charged particles that zip around the nucleus in a region called orbitals. Although they are much lighter than protons or neutrons, electrons play a crucial role in chemical reaction and bonding because they are present in the frontier. So those electrons that is present in the front represent a frontier orbital, which actually play a crucial role in reactions and bonding and are considered when studying about them. So their arrangement and movement dictate how atoms interact with one another, forming the diverse molecules that make up everything in our world. Together, these three types of subatomic particles, that is protons, neutrons and electrons, form the foundation of all matter, and understanding them is key to understanding the behavior of elements and compounds in chemistry. So now let's take a look at proton individually. So each proton carries a positive charge +1, that is 1 unit of positive electric charge. In terms of mass, protons are quite hefty compared to electrons, weighing in about 1 atomic mass unit AMU. They are located in a very heart of the atom, in the regions of the nucleus. And now the number of proton found in the nucleus isn't just random count. It is defined as atomic number of the atom. This atomic number is crucial because it tells us exactly what element we are dealing with. For instance, an atom with 1 proton is hydrogen, while one with 6 proton is carbon. So what's even more interesting is that during chemical process, the number of proton in an atom never changes. This invariant count is what keeps the identity of the element constant, regardless of the chemical process it undergoes. Right? So now take a look at neutrons, and is abbreviated like this way. So unlike protons, neutrons carry no electric charge, which is why we say that they are neutral. They have a mass that is almost identical to that of proton, roughly 1 AMU, atomic mass unit. So making them a significant contributor to the overall mass of the atom. Neutrons along with protons are found in the nucleus, the central core of the atom. Think of neutron as a glue. Proton, which all have the positive charge, naturally repel each other due to the electromagnetic forces. Neutron helps to counter this repulsion by adding a strong nuclear force that holds the nucleus together, despite their important role in nuclear stability. Neutrons don't affect the chemical properties of an element. That's because chemical properties chemical property and chemical behavior is largely determined by the frontier, that is electron, and the arrangement of the proton in the nucleus, right? The interaction between them. So if you want, okay, so additionally, during chemical reaction, the number of neutrons remain unchanged. So the identity of the element is maintained even if its isotopes might vary in the neutron count. Next up is electrons. It's abbreviated as E to the power minus, representing a negative charge. So now let's turn our attention to electrons, the tiny particle that play a critical role in the chemical behavior. Each electron carries a negative charge of -1, which perfectly balances the positive charge of the proton. However, electrons are incredibly light. In fact, their mass is less than 0.001 atomic mass unit, making them almost negligible compared to proton and neutron. Unlike protons and neutrons that reside in the nucleus, electrons are found outside the nucleus in area we call orbitals. that might resemble like this. So this is S, P, such and so on. That's not our concern today. So these orbitals are like a fuzzy cloud that shows where an electron is most likely to be formed. So it's just showing the probability, and they occupy nearly all of the space within an atom. So this is why, even though the nucleus is the most massive part of the atom itself appears so large compared to the nucleus. So one of the most important aspects of electron is that their role in chemical reaction. They are only subatomic particles that can be gained or lost during this reaction, which is why changes in atom's electron count lead to the formation of ions and ultimately determine how atoms bond with each other, the polarity. And understanding the behavior of electron is key to understanding everything from why table salt forms cubic crystal to how a complex molecule like protein comes together. So now what is a neutral atom then? If proton is charged, if electron is charged, how can this be neutral? So a neutral atom is one where the positive charge from proton is perfectly balanced by negative charge from the electron. In other words, the number of proton equals the number of electrons. So the charge cancel each other out completely. Take carbon as an example. A carbon atom has 6 proton and correspondingly 6 electron, which means its overall charge is 0. This equilibrium from charges is crucial. So not only does it keep the atom stable, but it also plays a key role in how atoms come together and form molecules. When the balance is disrupted, the atom can become ions. Example, cations and anions. So carbon also can form this kind of ions in certain conditions, which then behave differently in chemical reaction. So understanding this balance is fundamental to grasping the basics of chemical bonding and reactivity, so that we can control them according to our will. Next, let's talk about two very important numbers that describes an atom: the atomic number and the mass number. So the atomic number, symbolized with Z or Z, tells us the number of protons in the nucleus. For example, this number is unique to each element. So for example, every hydrogen atom has exactly 1 proton, which is why hydrogen's atomic number is 1 and helium has 2, right? So then we have a mass number denoted as A, which is a total number of protons and neutrons. So this is a sum of proton and a sum of proton and neutrons in the nucleus, giving us an approximate idea of atom's overall mass, while the atomic mass number tells us which element we are dealing with. The mass number gives us further insights into the specific isotope of that element. Together, these numbers help us understand the composition and identity of every atom. Now, sometimes atoms of the same element can have different number of neutrons, and these variations are what we call isotopes, right? So although isotopes are all the same element because they have the same number of proton, their mass number differ due to the differ due to the extra neutron, right? For instance, let's take a carbon as an example. Both carbon 12 and carbon 14 are carbon atoms because they have 6 proton, but carbon 14 has 2 extra neutron compared to carbon 12. So this is carbon 12. So this difference in neutron count gives them different mass numbers and slightly different physical property. So Isotopes play a critical role in many practical applications, such as in radiocarbon dating, where scientists use decay of carbon 14 to determine the age of archaeological finds. Understanding isotopes not only enrich our knowledge of the atom and atomic structure, but also provide us with a powerful tool for studying the world around us. Thus, a summary, and to summarize what we have just gone through. So, an atom consists of a nucleus containing protons and neutrons with electrons orbiting around it. A neutral atom has the same number of proton and electron, which keep it electrically balanced, and the atomic number tells us what element an atom is, and the mass number gives us an approximate idea of its weight. Isotopes are simply different versions of the same element that vary by the number of neutrons. Understanding these fundamentals is a key to further exploring chemical reactions and properties. As always, thank you and have a nice day.